This is problem 7-117 out of your book. We have steam going through an adiabatic turbine. At state 1, we're told, going into the turbine, we're told that we have 5 megapascal steam at 650 degrees C and 80 meters per second velocity. At state 2, coming out of the turbine, we have 50 kPa steam at 150 degrees C and 140 meters per second. And we're getting 8 megawatts of power out of the turbine. And what we want to know is, first, what's the mass flow rate of steam going through the turbine? And second, what's the isentropic efficiency of the turbine? Okay, so first we're going to find what is the mass flow rate of the steam. And to do this, we're going to start with an energy balance on our turbine. So the change in energy, the control volume with time, is equal to the rate of heat transfer to or from the turbine minus the rate of work plus the mass flow rate in and out times the enthalpy in at 1 minus the enthalpy out at 2 plus the kinetic energy in at 1. I'm going to go to the second line here, minus the kinetic energy out at 2 plus the potential energy of the flow in at 1 minus the potential energy of the flow out at 2. All right, now I'm going to do some simplifying here. I'm going to assume that my turbine is operating at steady state, steady flow, so the DDT term goes away. We're told it's an adiabatic turbine, so this Q term goes away. I'm going to neglect the change in potential energy of the stream in and out, and so that goes away. Now, just as a side note, remember that this whole last term here, this m dot term, is already a simplification because we start from m dot in at 1, theta in at 1, minus, clear that up a little bit, m dot in at 1, theta at 1, minus m dot out at 2, theta at 2, and we know, because we have single stream in and out, we know m dot 1 equals m dot 2, which I've written as just m dot. So we've already, and I've expanded these thetas as the sum of specific enthalpy plus specific potential energy plus specific kinetic energy. So just as a reminder, this is already a little bit simplified starting from the expression for our mass flows in and out. Okay, so now we're going to rewrite our simplified energy equation in terms of m dot, and this is m dot of the steam. And now we have the rate of work divided by what's left of our theta expression, so h1 minus h2 plus 1/2 v1 squared minus 1/2 v at 2 squared. Okay, so now we know almost everything here. We know our rate of work, we know our V1 and V2. Now we just need to find our H1 and our H2. Going to the next slide. So to do this, we're going to look to our steam tables. So when we look at state 1, we're going to do this as we always do by starting at our saturated water tables, and we're going to see that at 5 megapascals, our T of 650 C is greater than T sat, or alternatively, we look at 650 degrees C on those steam tables, saturated steam tables, and we see that our pressure is higher than our P sat. So either way, lower. So either way, we conclude that at state 1, we have superheated steam. And from table A6, we find that H1 is 3,783.6 kilojoules per kilogram. Okay, now we need H2, so at state 2, we do the same thing and we find that again we are superheated at the outlet of the turbine. And so again, from table A6, we find that, H2 is 2,780.2 kilojoules per kilogram. All right, so now we're ready to plug in and we're ready to calculate our m dot. So our m dot equals, now I'm going to be very careful with my units here. These are pretty easy to mix up because we're dealing with several different orders of magnitude here in terms of velocity squared and specific enthalpies and power. So what I'm going to do is I'm going to write my rate of work, my 8 megawatts, as 8 million kilogram meters second, meters squared per second cubed. And then in my denominator, again, you can do these in any units, you know, any way that the units make sense to you, but just be very careful to be consistent. Now in the denominator, I'm going to write these in terms of joules per kilogram, my specific enthalpies in terms of joules per kilogram. So 3783600 kilograms meters squared per second squared kilogram. Now again, that's just joules per kilogram minus 2780200 kilogram meters squared per second squared kilogram. And then again, I'm on the second line here, plus 1/2 80 squared, that's meters squared per second squared, minus 1/2 140 squared meters squared per second squared. Okay. So now when I calculate this, I get, and I'll write this in blue just to distinguish, once I calculate this all out, I end up with m dot is 8.03 kilograms per second. Write that a little bit neater. Okay, so that's my answer to part A. Now let's go to part B, where we want to find the isentropic efficiency of our turbine. So part B, isentropic efficiency. Now if you remember, isentropic efficiency is equal to the actual work that we get out of the turbine versus the isentropic work, that's the theoretical work if it operated isentropically, which we can write in terms of specific enthalpies as H at 1 minus H2 actual divided by H1 minus H2 isentropic. So we already know this guy, we already know H1, numerator and denominator, and we already know H2 actual. So we already know what the actual specific enthalpy is coming out of our turbine. So what we need to find is what would the specific enthalpy be of stream 2 if it was operating isentropically. So we need to find this for isentropic operation. And the key there is that S1 equals S2 if it's operating isentropically. And this is the key thing that's going to help us find our final theoretical state if it was operating isentropically. Okay, so we can find, first we're going to find what is S1, because then we can know what S2 is. We find that S1, because we already know that initial state, is 7.387 kilojoules per kilogram Kelvin. And now remember, the last critical piece that we need to recall in order for us to find this specific enthalpy at 2 is that P2 is set at the outlet of our turbine. Let me write that a little clearer. So P2 is set, okay, at state 2, but T is not. So going into our turbine, remember, at 1, at our inlet, we know P1, T1. We know what we're feeding into the turbine. But at 2, The only thing that's really set is P2, the pressure at the outlet. T2 is going to be dependent on how that turbine operates, and that's what we're going to use to find our second state. So the first thing we're going to do now is we're going to go to our saturated tables and look at 50 kPa. And what we're going to try to find is whether or not S1 here, which remember equals S2, we're going to see if this value is between the saturated liquid and vapor values at 50 kPa. So let's look at those values and write them down. So at 50 kPa, which again is our known property at the outlet of the turbine, even isentropic operation. So from the from the saturated tables, we see the saturated liquid value is 1.0912 kilojoules per kilogram Kelvin, and the saturated vapor value is 7.5931 kilojoules per kilogram Kelvin. So what we see is that our S2 for the isentropic operation is between these. So we know that if we were operating isentropically, we know we would have a saturated mix at the outlet. Okay. So next thing we need to do is we need to find what the quality is, because we're going to need that to calculate. We're going to need that quality to find the specific enthalpy at state 2. So we're going to use what we know. We know what our specific entropy is at state 2 in this isentropic operation. And we're going to write this. So this is the value. We're going to write this as, as a weighted average of SF and SG. Okay, so when I write those out, 7.387. And this is very similar to what we've done with other properties. This is how we find quality or how we find a mixture average for a saturated mix. So 1 minus X times SF, which is 1.0912 kilojoules per kilogram Kelvin, plus X times 7.5931 kilojoules Kelvin, and so what we find is that X equals 0.968. All right, now using that quality value, we're going to finally find our H2S. And we're going to do this the same way. So we're going to find H2S equals 1 minus X, which we just found, times HF plus X times HG. These values, these two, we can find from the table. And so when we plug in, we get H2S is 0.032 times 340.54 kilojoules per kilogram. That's the specific enthalpy of the saturated liquid at 50 kPa, plus 0.96, our quality, times 2,645.2 kilojoules per Kelvin, kilojoules per kilogram. And so that H2S value is 2572.2 kilojoules per kilogram. And now we're finally ready to calculate our isentropic efficiency. We have everything we need. So our isentropic efficiency of our turbine is 3,783.6 minus 2780.6, 0.2 kilojoules per kilogram over 3,783.6 minus 2,572.2, again kilojoules per kilogram, and that equals 0.828, or our isentropic efficiency of our turbine is 82.8%.